All right, so this is going to be the starting of the third week now. All right, so we have been through a lot of stuff. I think that's already 4 lectures. All right, the time really fly. So I think we can finish this module in thermodynamics. I think maybe within next week already. Yeah, so I think maybe next time that we see each other, then maybe we can discuss when is going to be our first exam date. That's like sounds like a good plan. All right. And once again, just to be clear, for those of you that forgot what we sort of agreed, so you guys can come up with any date that you like. Okay. So just like you pick a day and just pick any convenience day, and then we will just set up the first exam date, and that's it. Okay, so it's going to be quite flexible, and well, it can be any day. It used to be even Sunday. All right, and just to remind you that the format of the exam is supposed to be, I think it's still take home. Right? You have like at 12 hours. So the exam will be released maybe in the morning, for example, and then you can hand it in 12 hours later. Okay. So, but anyway, this schedule can be adjusted. Okay. All right. Second thing, I don't know. I just had a chance to discuss with uh actually this portion might not need to record just yet. But anyway, um as you guys like studying at home or online? I mean, online or on site? I mean, you guys at on campus at this point? I don't know. I just realized that I thought that MUIC policy is just having all the lectures to be conducted online. And that was just like, just blew me a little bit that I just realized that some lectures are sort of currently being held on site. So that's my sort of confused information. All right, but anyway, the point of this one is just so you know that at any time, I mean, when the situation is getting better and you guys seems like, hey, Ajahn, it's already too much that we're going to uh, see each other through Zoom, then just let me know. Okay, so maybe that it's time to get together on campus if you guys feel it's safe enough, and we sort of like comes together as a conclusion that hey, everyone seems to be okay with this, or majority of class feel comfortable going to campus, on and on. All right, just keep me updated on that, because right now I'm still sort of like keep the online format most of the time, just on to be on the safe side. That's all. Okay, sounds good. All right, so I'm not sure what you guys preferred, but I hope is okay. Okay, this will be weird. But okay, but I did the hybrid type before. That's not so good. Even though I tried so hard, but it seems like I cannot manage to pay attention to both sides of the class. It's like, it's like, okay, you guys here in the classroom, and then what about you guys at home, on and on. It's still not very, I don't know. It seems like students at home seems a little less being paid attention to. Okay, all right, let's get back to our business here. So we're going to have a lot more fun. And as promised, we are going to eventually arrive at the best heat engine in the universe. All right, you're going to have a chance to see that. Okay, and as you can notice from the outlines here, there is another word that you probably have heard from time to time of the entropy. So toward the ends of this module, you have a chance to talk about the entropy. All right, and eventually the second law of thermodynamics. All right, that will be very good. Okay, guys, are you ready? Okay, all right. So what we are going to start today's lecture, and I think majority of today's lecture is going to be heat engines. But the good thing about this one is we are going to use everything that we have learned from the past week and apply to this. All right, with a little bit of additional stuff that you just throw in, so you can explain how well the engine perform just a little bit. But beyond that, first law of thermodynamics will provide you pretty much everything, allow you to do some, or actually even all of the analysis that you need to sort of, understand how engines work, right? Thermal engines, yeah. Okay, all right, here we go. So I think this is going to be the grand the grand opening or the main diagram that you are going to refer to this as like a big picture of what is about. And this one represents how the heat engine works, all right? And as the name implies, is an engine that operated by heat. So that means there must be some energy flow. And to be able to operate this engine, you need difference in temperature. So the general idea of this whole thing is just, right, because once we kind of know that there is an energy flow from hot to cold all the time, every time, and the nature seems to do this everywhere. So every time you have a hot stuff and cold stuff in thermal contact, there is an energy transfer. Everyone seems to okay with this, no problem. But then here comes the idea. Can we utilize that? Because now we understand that the heat is energy transfer and it's always go from hot to cold. Is there a way that we can tap into this and then steal, well, maybe steal is not a good word, but at least redirect part of that flow and then turn it into something useful for us? Does that make sense? Okay, so that's why this diagram is going to be our main diagram. So think about this. You have hot reservoir. So now we know when you say hot, mean temperature is high. Okay, that's good. No big deal. Then you have a cold reservoir. So that's where you have a low temperature right there. Okay. Now, if you put these two reservoirs in contact, you are definitely going to get energy flow. It's going to flow from hot to cold. Here comes the role of the engine. So you are going to squeeze in an engine. All right, I'm going to put it there. Well, okay, John, I know that there is something flowing. I am trying to redirect a little bit of that. It will be even best if I can redirect that 100%. Would you like that? Whoa, so that will be so good. Okay. All right. So if that is possible, that means you can pretty much tap into the energy that's already built into our nature, and then you just have run things indefinitely. That will be so good. And that was humans' dream, actually, that you can do things indefinitely without have to invest anything at all. But you will see very soon that this is not possible. You have no way. This is so weird. We are in the universe that nature does not allow you to take everything. All right. So that means you still have to somehow have some leftover. Right. You can, redirect portion of it, some of it, but not 100%. All right. So that is the reason why you still have some things that you have to throw down to the cold reservoir. All right. So I hope you get the big picture of what we are trying to do. It's so simple, guys. You bring in the hot reservoir, install the engine, draw in the energy from the hot, and hopefully you can do some useful work. So you're trying to do this. All right. So hope that that engine can operate something, lift some weights, turn some wheel, and then you still have some left over that you cannot bring it to something useful, and then you have to discard it at the lowest temperature. Does that sound cool? All right. So once you have this grand structure stuck in your head, what else? Everything is still under first law of thermodynamics. What does it mean? All right. It's a conservation of energy. So think about this. There is a heat flow in. That's amount of energy flowing in. There is a portion of the energy being transferred and sort of changed, converted into useful work, and another part thrown out. Conservation of energy, guys. Okay. It means whatever comes in must be equal to things that go out. You guys with me? All right. And just to be safe that we don't want to worry about heat flow in is positive, heat flow out is negative, on and on, just put an absolute sign into it. Why not? Okay, so we don't have to worry too much about, because we always know that heat must be flowing into the engine from the hot side leaking out from the cold side, and the work done supposed to be something positive that coming out from the engine. So from the conservation energy, in must be equal to out. So you say total amount of heat flowing in must be equal to the one that you have to throw out, yeah, plus the work done by the system. Isn't that easy? Right? Of course, in equal to out. And because we are focusing on the engine, so what we really want is to express the work done. So with the work done, because we already defined this one to be the work done by the system, you don't have to keep writing the absolute sign. The W is already W by the system, and then we define everything from integral P dV. So everything is good. So the left-hand side, we just left W there. It's just going to be the difference between the heat flowing in, subtract the amount of heat flowing out. Cool. And you are done.
Okay.
Guys, that's it. That is the today's story. Isn't that amazing? All right. So what we really want over here is second thing, because we want this engine to operate on and on and on and on. So the process that you're going to throw into this engine is supposed to be something that runs in cycle. Does that make sense? So now you can imagine, okay, John, that's the car engine. That's why car engine has to come in cycle, and, you know, come and over and over. And now you start to understand why you need the fuel combustion in the car engine. Why do you have to combust the gas? Because you want to take here, the engine's supposed to operate between hot and cold. So when you combust the gas, you generate like 1,000 Kelvin of gas after the combustion. That's you start up like you release the chemical energy, and then you get to something so hot, and that serve as your hot reservoir. Does that make sense? And the cold reservoir is just in front of your car, right? When you know, okay, you look at if you touch the front of your car, and then you see your engine running so hot, and that's where the cold reservoir is. So there are some heat that is releasing out from your car, from the car engine. That's why the car engine running hot, because that is the leftover energy that you cannot do anything with. Does that sound good? All right. So I hope you sort of like see the whole picture of what the heat engine is, and then you can just relate this one to your car engine that you have already seen around you. Okay. You combust the gas, take the chemical energy and everything, whatever, burn it out, and start it out the hot source of energy. Hot source of energy. That's all right. It sounds like, you know, okay. But anyway, start with like something very hot, and that serves as your hot reservoir. Okay. And the engine try to take the flow from that hot reservoir and, you know, turns part of it into something useful, which turning the wheel, and you drive the car. Okay, guys. So good thing about the cycle stuff is we learned from last time, everything that you come in cycle lead you to delta U to be zero, because U is energy. So every time you arrive back at the initial point, no energy change. Okay, so that means good. Isn't that nice? From the first law of thermodynamics. So that means, oh, I don't think I need the delta sign there. So amount of heat is just a W, but the reason I put the delta in here, it take a different meaning. The delta over here, it's pretty much mean this. Okay, let me sort of put a little highlight there. Sort of here. The delta mean it's just a difference between the heat flowing in and heat flowing out. Does that make sense? All right, because in general, you have to take into account all the heat that's involved within your system. And because right now you have two sides, the in and the out. So I put delta there. Is sort of like, it's not the same as a delta U per se. It's a delta in the sense that you have one that's coming in and the other one going out. So you just take the delta, take the difference, okay? And the rest goes into the W that you're just seeing over there. All right, guys. So that is like, I think maybe it's already too long of the introduction, but that's what I want you to see. And what I can actually come up with a quantitative conclusion of how well an engine is working is just by define this simple. I think this is a very intuitive parameters. It's called efficiency. If I'm asking you guys, hey guys, what is your learning efficiency at this point? what is your physics efficiency? I mean, physics study efficiency or learning efficiency. So the concept is of efficiency is a simple one. What do you get over what you are provided? Does that make sense? So like I'm teaching an hour, how many minutes that you can take into your understanding and it's stuck in your head, right? So the concept of efficiency is what you get over what you have to provide. Okay. So in this case, what you are getting is, of course, and I want to get this work. The more of the work done by the gas, the better. The more of the work done by the engine is better. We want more work. Okay. And what is the thing that you have to supply to this engine? Well, of course, Ajahn, I have to supply this. Is the amount of heat that is the source of everything. So it's the hot reservoir that is providing the energy, to supplying the energy to the engine. Does that make sense? All right. So that means the concept of efficiency, that's why it's so straightforward. What you are getting is W, but what you have to prepare to get this thing going is the Q hot. And now you can manipulate this expression whatever you like. You now know that the work done is just the difference between the heat flow in and the heat flow out. And then you just take the ratio and then you can say it's a 1 minus Q cold over Q hot, whatever, up to you. All right. But I hope the concept of thermal efficiency is now very easy to grasp. It's just what you get or what you have to supply or provide to the system. Okay, cool, guys. I hope.
Okay.
All right. Now, let me ask you sort of like just, just get like a rough idea. You would, let's say, talk about the car engine. Let's talk about even the diesel engines. Yeah, mostly you can see in the truck or whatever. What do you think? What kind of efficiency that you get it out of the car engine? Okay, don't look too far. I already write it down for you. It's right there. Believe it or not, you only get the efficiency only like it's less than half. I'm saying it's 35 to 40. Even the diesel engine that you already think like, okay, this is already very efficient, right? But that give you up to only like 40, the best case scenario, probably 40 something. So that means all of the energy that you supply to the car engine, more than half is being thrown away. That's why the engine runs super hot. Yeah, because that whatever you touches at the surface of the car engine and you feel, oh, that's running really hot. That's the leak. That is the heat that pretty much useless. Too bad, nothing you can do. Okay, so and this is the reason why the movement to electric car, it's unstoppable, because the efficiency that you can get out of an electric car is going to be all the way up to like 80, 90 something percent. All right, even though this number might be depends on the perspective of whoever speaking of the efficiency, but it's going to be well better than 40% that you are seeing. So it's way better. Okay, and in terms of benefits that you're going to get out of something else, the number of like parts get fewer. You don't have to worry about transmission or whatever like stuff that you have to mechanical stuff that you have to link those all together. It's just a motor attached to a wheel. Once the motor turns, the wheel turns. Let's make everything so simple. So everything else sort of lead to that electric car and other stuff. But anyway, who knows? All right. Right now, we are in the hybrid scenario. So you have like a hybrid engine and all that stuff. Try to improve this efficiency number. Okay. So we'll see. All right. But it seems like everything, seems to go to with electric somehow. All right. Let's take a look at a quick example over here. You have a gas engine burns 0.2 gram of fuel and delivers 2,000 joule of work per cycle. So this, you can imagine this scenario, just exactly what is going on inside a car engine. Given the heat, given that the heat of combustion, that's what it is equal to 5 times 10 to the first joule per gram. So this means every gram of fuel that you burn, you're going to get 5 times 10 to the fourth joule of energy out of it. Okay, very good. Find the heat discarded in each cycle and what is the thermal efficiency of this engine. All right, guys, try this one. I want you to try this. Just sort of like, I mean, it looks simple, but I want everyone to have like a, you know, some sort of like infrastructure of things that we are about to do. All right. It's going to get more complicated very soon. All right. So what I want you to be able to do this is just like, you know, think of this diagram as the main diagram, even though now it looks so messy. All right. But that's what it is. So first you have 0.2 gram of fuel. So let's at least calculate how much energy you are going to get each cycle because you're burning 0.2 gram. So let me write it like the total amount of energy. Let me put E for now, right? The energy per cycle is going to be, you just take the L, multiply by, let me put the M here. So if you look at the equation, and if I write it sort of like this, and if I turn this energy into Q, it's the form of the latent heat, you know, that you saw before, but this is just a simple concept that just take the mass of the fuel and multiply by the amount of energy per unit mass, and then you get the total amount of energy coming out of it. Okay, so the total amount of heat that is going to flow into the engine is going to be 0.2 gram multiplied by 5 times 10 to the 4th joule per gram. All right, cool. So this is 10 to the 4th. All right, so this is it. So every cycle with the combustion of that fuel, you get 10,000 joule. Cool. All right. So let me sort of draw the diagram on the side here. And you can say now, there you go. That's the heat flow in. Let me write like this, 10,000 joule. So because this one is supposed to be after the combustion, the gas will get hot. That is Q hot that we are talking about. You guys with me? All right. So this is a Q hot. And now it says every cycle, this engine delivers 2,000 joule of work. So that means this can provide 2,000 joule of work. So from the conservation of energy, you're going to have the leftover of 8,000 joule, and that is being treated as the Q coal. All right, so that's it. So you can say the efficiency is going to be work over Q hot. And if you don't have to worry about the sign, you can just put absolute sign here if you like. Okay, and then you just say it's 2,000 over 10,000, and that is 0.2, or you can write it as 20%. Okay, so that's it, guys. The answer for this one is, what about the heat discarded? Discarded 8,000. That's right there. Okay, what about the thermal efficiency? Is right there, 0.2. Okay, and efficiency has no units, of course, because you take energy divided by energy. It's just a number, sort of give you the level of efficiency. All right, so I think you have enough, sort of like what it means by the heat engines. So before we dive deeper into that, I think this is a good question, Bo Ajahn. All right, we kind of know that heat flow from hot to cold, but what if we want to run everything backward? We want to go in reverse. Is it possible? That's the question. Yeah.
Okay.
The answer is, of course, it's possible, but it's not going to come naturally because heat flow from hot to cold by its own. But if you want to have things go backward, how can you do it? The idea is just like when you deal with water in fluid mechanics, for example, we know that water falls from high to low. Okay. Now, if you want to bring the water from low to higher level, you need a water pump. Does that make sense? So over here, heat flow from hot to cold. If you want to bring the energy from cold to hot, you have to have heat pump, and that's it. So introducing heat pump.
Okay.
No need, no clap here. All right. So the heat pump is the engine trying to bring the energy from the coal. Here we go. And dump it to a higher energy up top. And the way to do that is you have to supply now some energy to operate this pump. So that's why the sign of the W is going to go reverse as well. You see that? So it's just a heat engine, but every arrows that you are seeing is just go backward. So that's mean in this case, the W is going to get reversed and then put it back into the pump. All right. And this is how your air conditioner works. Okay. So to run air conditioner, of course, you have to, turn on the electricity and turn on the switch on and on. So it means you need some external supply of energy. But the whole idea is the air conditioner is trying to move the heat or move the energy, right? Move the energy from inside the room to the outside. And right now, as you can see, inside is colder than the outside. So air conditioner is trying to transfer the energy from the colder place to an outer place. Okay, so the air conditioner is the heat pump. Same thing with the refrigerator. Inside the refrigerator is the cold temperature. The back of the refrigerator is hotter. Okay, so you are removing energy from the colder place and release it to the hotter place. Okay, sounds good. All right, so what if, and I would like to ask you, like, how well this air conditioner or the fridge is working. So what do you have to come up with the same concepts of efficiency? So you probably can say, well, Ajahn, that's okay. I can sort of look at this one and then I can understand that it still underlie the first law of thermodynamics. I mean, the underlying first law of thermodynamics still hold. So what you get over here is you still have Q hot equal to the W plus Q cold. See that? All right. And maybe this is the, well, maybe it's just my mistake. Oh, I'm not sure. Or maybe I got this one from the textbook. It's kind of weird. All right. But yeah. Okay. I think in this case, the W is kind of like going inward. So there's some external work done into the system. So you might even need to put absolute sign in there, I guess. Otherwise, it will be weird. All right. Just to be clear, let me put absolute sign there. All right. Just to make sure that we are just considering just the magnitude, just the number. Okay. So what you have over here is now from the first law of thermodynamics, heat Q hot, the Q hot must be equal to the sum of the Q cold and the W. Okay. So that's fine. But then if you would like to define your efficiency, just like what you had done before, it's just what you get over what you have to provide. Is that right? So what you think, what are you getting when you are running air conditioner or and refrigerator? What are you getting? Of course, what you're trying to get is this. The better the Q that you transfer from the cold part, the bigger the better, right? Because you want to transfer energy from the colder part to the hotter part. So what you are trying to get is the Q cold. What do you have to supply? Well, of course, Adan, you have to supply this, the W. That's what you're supplying. Okay, so that's why you just divided by the W here. So that's good. That's done. Okay. Okay, using the same concept of efficiency is right there. However, the bad thing about this one is the efficiency usually makes sense to you guys when it go between 0 to 1, right? Because efficiency is 1 means 100% efficient. When efficiency is 0 means you get nothing out of it. But it turns out this ratio can go beyond 1 because it's just a ratio between the Q cold and the W. So just to make things sort of like, not mixed up with the efficiency definition, so they try to come up with another word, and that's what this is the coefficient of performance. Okay, so that's by definition, that's what it is. Okay, so that's just so you know what we have based on our basic definition. You can pretty much explain any kind of engine. All right, running forward, you have heat engine. Running backwards, you had heat pump. And if you want to have efficiency, that's fine. No matter what is the concept stays the same. What you get over what you have to supply or provide to the system. Okay, but we have like a quick note saying that, all right, in case of the heat pump and in the case of the refrigerator or air conditioner, we just rename it and call this efficiency to be coefficients of performance. But then there is the one final, annoying part of this one is we mostly use this coefficient of performance that they are doing the cooling stuff, right? The refrigerator, the air conditioner. So that's why we put a sort of like a note saying that this is the coefficient of performance in the cooling mode. Why? in some country that's, things are super cold, we don't want air conditioner anymore. It's so super cold. So actually it's going to be the heat pump that is running in the opposite direction, in the sense that they want to pump the heat from the outside, which is already cold. Maybe it's snowing already, or it's already in winter. And then you want to warm up the room. Does that make sense? So actually you might be looking at the heating mode of a heat pump. So if that is the case, you have to replace Q cold with the Q hot, because in the heating mode, what you are expecting as an outcome from that heater is this dude right here. Okay, does that make sense? All right, so I hope I give you like the grand conclusion of what does it mean by efficiency in all cases. All right, but for us in Thailand, at least, I think we're going to mainly use the cooling mode, because the heating mode is kind of weird. But Ajahn, why do you need the heat pump in the heating mode? You just burn something and then you're gonna already get super hot, right? Okay. Okay. So, well, there are some other purposes if you really, when you really want the heat pump in the heating mode. But I hope you understand the whole definitions of the efficiency. Okay, sounds cool. I don't know. I'm วันนี้พูดรู้เรื่องไหม Okay, still okay with me? All right. Whew. All right. Okay. All right. Just let me know if there are some technical issue or whatever. Right. Okay. All right, guys. Now, this is what I promised you last time. It's the time that we're about to dive in. Okay. So once we understand the heat engine, how to calculate efficiency, it's time to build our engine properly. Properly. But before we get the proper build of this one, there is one question that I sort of like threw at you last time. It's not a question, but it's something that I'm going to tell you the story is, what is going to be the best engine in this universe? Oh, all right.
Okay.
All right. So what kind of engine that you think is going to run the best? And now we know 100% is impossible. No way. All right. That's impossible. But what is going to be the maximum numbers of efficiency that you're going to get? Before we can even answer that, I have to tell you this story first. And this is so weird. And somehow it gets you to talk about the reversibility of a process. So that means you have to consider a reversible process and irreversible process first. And you will see why right now. Look at this. Everyone knows. Go back to remember, if you remember vaguely, we have this system before. You have a gas in a tank that is already insulated, no heat exchange. This one, okay, John, I remember this. No heat flow. The container cannot be expanded or contracted, so no work done. Okay. And this one will not give you any internal energy change. And once the membrane breaks, gas just fills up the whole tank, boom. But nothing happens. According to the first law of thermodynamics, it doesn't do anything. Temperature stays the same, no heat, no work. The only thing that is changing is just the state of the gas. But the temperature is fixed, but the pressure might be half the original, but the volume expands twice as big. So everyone follows. So far, so good. Now, we know this is an irreversible process. Everyone knows, Ajahn, it's not going to be able to have all those molecules that running on the right side of this figure and just collectively like, hey guys, let's stay in the bottom half of the tank. The probability is super, 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 super low that you're going to have like, million of molecules just coincidentally appear just the bottom half of the tank. Okay. You might have to wait like longer than the age of the universe for this to happen. So I would call this not possible. So this process is already irreversible. Cool. All right. Now look on the right. Now, if you change your mind, Bajjan, don't take that system to be your system of study. Let's take this one instead. So you have the same gas, but then you attach to the engine reservoir just like what we had before. So this one, temperature stay fixed, just like what you had last time. And we remember that if the top portion of this one is attached to something that's movable, we used to have a piston before, but now let's say you have like some sort of like a lid, and that lid can be moved up and down at will with no frictions and everything, right? Just this is in your imagination. What you have over here is you can actually squeeze down the gas or let the gas expand just a little bit by imagine that if you're pouring sand, this is the weird one.
Okay.
All right. It's just like you're pouring a grain of salt if you want to, bring it from the kitchen or whatever. Okay, let's something super light. And then you just pour it onto the lid. So you can compress the whole lid down a bit, compress down the gas slowly. But then you say, but Ajahn, I changed my mind. I want to get everything back to the original position. You can just pick up each grain, right? Grain by grain, and let the gas just expand slowly back into the original position. And then you can reverse this whole thing. All right, I'm just want to do it again. All right, pour in some sand in there and then get everything down again, on and on. So this process is trying to show you that this is a reversible process. Okay? All right. And you can see that by having shown you this one lead to the word that you have seen once, the quasi-static. Right? So when you do things very, very slowly, that's when you're like, okay, all right, things, all right, adjust, make sure the temperature is nice, pressure is nice, volume is okay, it's already done, and everything can be measured perfectly. Things has to do in a very, very slow manner. And that's what it pretty much relates to the word quasi-static. You have to do everything in like, move a bit, stop, move a bit, stop, move a bit, stop. That's what it is. But anyway, our point right now is the reversibility. The scenario on the right is reversible. On the left is not. But here comes the kicker. It turns out every process in this world, I'm not so sure if I can say in this universe. Maybe that's just a little bit too much. Who knows? Okay, but anyway, just stick with what we have around us. In this world is irreversible. You're getting older. That's not reversible. Okay. All right. People grow. Okay. Things breaks. Stuff get aging, broken toward the end. Electronics will fail eventually, something like that. So things in our world pretty much irreversible. Okay. So what's the point, Ajahn? The point is this. Now let's get back to our thermodynamic system. Here, the reversibility and irreversibility comes into play when you have this scenario here. Look at the ice. If you have an ice in a metal box and the box is hot, 70 degrees Celsius, the ice is at 0, it's going to melt. And at the end, you might get mixture between water and the box at about 40 degrees Celsius in the middle. But as you can see, whatever the heat that is involved within this process is going to be used to melt the ice, and this is irreversible. Make sense? No way that you're going to get ice and the metal box get hotter from the right figure to the left. This arrow is not reversible. Oh, okay. It's right there, just going one way. Okay. But now look at the bottom. If you have a metal box at 0, same temperature as the ice, then microscopically, there's no way for you to be able to tell that, hey, the molecule of the water stick around as the ice all the time because it's already at the phase change temperature, the phase transition temperature. So that means at this point, at 0 degrees Celsius, microscopically, I don't know, sometimes it could be water-like, sometimes it could be solid-like, who knows? All right. And everyone knows during this process, you have a latent heat of fusion involved in the melting process. But because the environment, which is the metal box right now, is still at 0 degrees Celsius. So that means that might be have like, they have like a microscopic exchange of something and then they can exchange it back or whatever. So when they are operating at the same temperature, the latent heat of fusion that involved in this process, it doesn't really go anywhere. is still within this box and the ice system. Does that make sense to you guys? So the arrow go both way. You can still go back and forth, as long as your environment, environment from the perspective of the ice is at 0 degrees Celsius. So the bottom scenario is a reversible scenario. Okay, so from the perspective that we're going to use next is this. The reversibility seems to have some connections with the temperature. You see that? See that? Oh, not that one. Yeah, this one. Okay, let me highlight on the left. Sorry, guys. Just wrong side of the, here we go. So it looks like if you're trying to operate between two different temperatures, the heat that involved in that process is going to be pretty much gone. When I say gone, I mean it's once being used, it's gone. It's not gone, but gone is it's already been used. And once the heat that already been used, you probably won't be able to execute something that is going to be, what happened? It's, what's going on? Oh, okay. Yeah. See, once the heat is already gone, it's just like you're already at the bottom half of this diagram right here. It's just like, okay, it's already discarded or something. It's already gone. Okay. So it's just like already down here. And it's just like, bye-bye. So on the other hand, when you still have a reversible process, the heat that involved in that is still sort of like, lingering around, still stick around. So one day, maybe you can still make something useful out of it. Does that make sense? A little bit, I hope. Okay, so that is why it seems like if you're trying to operate between two big temperatures, the heat that involved in this process is going to be the heat that you cannot make use of it. Or you can think of it like, okay, you're going to lose that heat to something that's not going to be useful anymore. But if you try to operate things at the same temperature as the whole system, at the whole things that you are looking at, the heat involved within that process, it's still with you. It still flow back and forth. So hopefully in the future, well, it's still within your system, and then you might be able to do something with it. Okay. And remember what we defined the efficiency. The efficiency is we want to minimize the loss. We don't want a lot of loss. We want things to be very useful. So that's why more of this is bad. You care with me? Okay. So what you really want to do is to get the best possible. You try to make as small of the irreversible portion of this. Okay, irreversible portion is you try to minimize the Q that involved in the change in temperature. See, temperature change. Okay, there's a change in temperature here. So you try to minimize the heat that happens during times of the engine operation that you have to deal with the temperature change. You try to minimize that because this heat sort of like not good. Okay. So to deal with the heat, the best way to do it, let's deal it when the temperature is at the same temperature. This heat is still all right. So this is pretty much like the conclusion I want to make is we try to combine these two effects and try to maximize the efficiency. Does that make sense to you now? Okay. So conclusion is when you change the temperature, try to minimize the heat in that process. Okay. But because you cannot avoid doing the heat exchange because it's a heat engine, you need to exchange. Let's do it in an isothermal process.
Okay.
Cool. Start to feel something here. So this is it, guys. Conclusion is this. So if there is a heat transfer, you want it to be in the bottom case when you have a heat transfer, right? So you do it under isothermal process. But then because you cannot avoid changing in temperature because your heat engine has to operate between hot and cold. So somehow you have to change the temperature, then otherwise then there will be no engine. So if you want to change the temperature, let's do it without any heat exchange. So you just minimize by take this to be 0. And what kind of process is this? Yeah.
Okay.
Welcome back. Adiabatic process. Why do you have to clap on this one?
Okay.
Okay. So if you have these two processes in combination, making you an engine, then that engine will run at the highest possible efficiency. And the one who found out this fact and come up with the engine that combines the isothermal process and adiabatic process is Carnot. That's why we name this engine Carnot engine. Welcome to the best engine in the universe. Okay, and how does it look? You guys still remember isothermal process is a process that's running on a single isotherm. Yeah, remember that? All right, that's an isothermal process. And adiabatic process is a process that's steeper than the isothermal process. Now you want an engine that only operating between just only these two processes. Here we go, guys. Welcome to the this is a big crowd over here, guys. The Carnot engine, the engine that is at the peak of all efficiency attainable to human. This is it. This is the highest efficient engine running between two temperature. How does it look? Start from here, guys. Okay, okay, let's expand the gas because you want to pull in the heat, right? The key is you need the heat to flow in. Okay, having your main diagram with you all the time. So you need the heat flow in, Q hot. You have to draw in some heat. So we just said every time that you want to have a heat transfer, do it isothermally. Got that? Let's do it. During this pull in the heat, I'm going to do it using isothermal process. The one that I'm highlighting red at this point. Here we go. See? Isothermal. Cool. So during that time, here, I will have a heat involved, and that's your Q hot. I'm pulling in the heat. Now, you're going to have to operate between hot and cold. So you're going to have to jump down to a lower temperature no matter what. So during that jump, you're going to have to avoid heat at all costs. So what you are going to do next is, all right, guys, I'm going to jump down to a lower isotherm, but then I'm going to do it adiabatically. Here we go. Now I'm already lying in the lower isotherm. So that means I already at a lower temperature. With me, guys? But because I would like to have this engine run in cycle, so I have to shoot back to A. I have to go back to my original position. Plus, I'm going to have to throw out some heat because I have to have some heat discarded anyway. So during, oh, sorry, Q cold. So during this process, I have to have a heat transfer once again. So during the heat transfer, what do we do? Yes, we do it through isothermal process. So I am going to move back a little bit here, the blue in the bottom here, see that? And during this portion here, I discard some heat, and that is our Q cold. And once I'm done with that, I'm going to have to jump back to a higher temperature. This means I'm shooting back to point A. So what I'm doing is I have to change the temperature, and we already said changing the temperature, please do it without exchanging any heat. So I'm going to jump back, woohoo, adiabatically back to A. That is Carnot cycle.
Okay.
And with this, it's a two isothermal combined with two adiabatic process. You get the best engine in the universe that's operating between two temperatures. Those two temperatures are, the T hot and the T cold. See, you're going back and forth between these two isotherms. All right. And what is the conclusion, Damo? And then what is the efficiency? All right. And then, Adan, are you serious? Well, yeah, I'm serious. You have to do this. we kind of okay about that. Isothermal process, we know how to do. Isothermal process, we know how to do. Adiabatic, we know that PV to the gamma is constant, and I can convert it into the relationship between the temperature and the volume, blah, blah, blah. But then I don't want to prove this one to you. It would spend, 30 minutes, maybe 15 minutes showing you how these four equations rearrange and then what kind of relationship that you're going to get. But here comes the conclusion, and you will love this. Conclusion is so simple, guys.
Okay.
From all these four equations, the Carnot engine lead you to this. For the best engine in the universe, the ratio between Q cold and Q hot is just a ratio between the two temperature that this engine is operating. And that lead you to Carnot efficiency, replacing the ratio between Q cold and Q hot with the T cold and T hot, and you are done.
Okay.
Cool. All right. And then after the break, I will explain why can't you use your body temperature to charge your smartphone. All right. And that's because of this limitation that we are seeing right here. Sounds good? All right, guys, take 10 minutes break and when we reveal the truth behind the nature. All right, see you in a bit, guys. All right, so once we have already seen this results, so in terms of calculation, you guys are supposed to be like, okay, John, this is good. There's not a lot of problem here because the conclusion is simple. Okay, it's just a ratio between temperature that give you the ratio between the Q cold and Q hot. It's cool. Now, let's compare this to, I mean, because we are not trying to do some sort of like a thermodynamics in engineering or whatever, so you don't have to worry too much about the detailed analysis of this one. But if you look at the textbook, they have a comparison between the Carnot cycle and something that has a name. It's don't worry about the name. It's an Otto cycle, and this one can be sort of like represent what the gasoline engine is operating. Okay, as you can see, I mean, the key result that I just want you to compare is just this. See, it doesn't look like Carnot engine whatsoever. You have constant volume process combined with some adiabatic process. So what you can expect from this one is if you calculate the efficiency of this process, it's not going to beat Carnot cycle because the Carnot cycle now is our maximum possible efficiency. That is our ceiling. Nothing is going to go beyond that. Isn't that amazing? I thought this is sort of like wow, wow, wow moment here. All right. So what you're getting over here to consider is this. All right. Let's warm things up a little bit, and then it will be clearer why we cannot use our body temperature to sort of, charge the USB port or whatever. Three engines operate between reservoirs separated by in temperature by 300K. So it means these three engines running between hot and cold reservoirs that have 300 Kelvin in separation. The engine A is 1,000 to 700. Engine B is 800 and 500. Engine C is 600 and 300. So the question is just want you to rank the engines in the order of theoretically possible efficiency. So that's the Carnot efficiency, right? The efficiency if you were to use a Carnot engine operating between these two given temperatures, okay? Which one? Okay, let me ask you, which one will give the highest efficiency among the three? What do you think? Right, they are all separated by 300 Kelvin. And of course, you can see that the B come in between. So it's not either engine A or engine C, right? So if you want to go straightforwardly, we already had a formula. The efficiency that has the highest possible value is the Carnot efficiency. I can put subscript C in there, and it's going to be equal to 1 minus, okay, according to concepts of efficiency, is a Q cold over Q hot. Yeah. And now by having the Carnot engine operating between these two temperature, I can turn that ratio of the heat into the ratio of the temperature. And now I can just plug in the numbers. Yeah. All right. I can try engine A. Okay. Let me put engine A. It's going to be 1 minus 700 over 1,000. And that will be 1 minus 0.7. And this engine running at 0.3 or 30% efficient. Let me go engine C. It's going to be 1 minus 300 over 600. And that's going to be 1 minus 0.5. And that's 0.5 efficiency. So it's 50%. So in this case, you will say engine C will be the best. So the highest is going to be C. And the lowest is going to be A, and B come in between. Okay, cool.
Okay.
All right, but now I want you to think in this way. If you have energy reservoirs that are separated by 300 Kelvin, the sort of like this exaggerated example is if you have engine D running between 1,000,000 K and 1,000,000 subtract 300K. See? All right. Oh, maybe this is a little bit exaggerated, but you'll see my point. So what you're seeing over here is these two temperatures are separated by 300K. But because you are dealing with 1,000,000 Kelvin, to have something different by a fraction of a million, you won't feel a thing. So that's why this is going to be super low efficiency. You guys with me? Sort of get an idea. So because if you are like a whatever, an alien, sort of live in 1,000,000 Kelvin temperature or million Kelvin environment, to have the temperature different by 300K, you won't feel anything. So when I say I feel nothing means I probably cannot make use of this difference. It's the difference is super small. So that's why in this case, what you can see, the efficiency will be 1 minus almost 1. Oh, sorry, that's not the terminology the symbol that I need to use. Okay. E is going to be 1 minus million minus 300 over million, and that is approaching 0. Cool. On the other hand, if I look at the engine E, I'm running between 300K and 0K, which is okay. It's impossible. I know. All right. But just saying. So this is the case that you're going to get 1. That's 100%. So why? Okay. I mean, just to be more realistic here. So what I can do is I can do what Ajahn, that's not possible. So let's do, there you go. Why not? Okay. 300.1 Kelvin and 0.1 Kelvin separations of 300 stays there. But now you are in the environment that is so super, super cold. So the 300 Kelvin difference will, oh, wow, that's a lot of difference. You guys with me? So in this case, the engine E will run very, very, it's like almost 1 efficiency. So that's what I'm trying to give you an idea of when you want to make use of something using the heat engine by the heat engine, you need temperature difference. But that difference have to be in comparison to the environment that you are in. Okay, 300K in 1,000,000 Kelvin environment is nothing. So in that environment, you're not going to be able to generate some useful heat engine whatsoever. But then now back to like something super cold, almost at 0 Kelvin, 300 Kelvin is huge. Okay, and of course, from these expression of the Carnot efficiency, now you can see that the requirements for you to have 100% efficient engine, see that? Because now it's a ratio between T cold and T hot. To make this go to 0, to make this go to 1, you have to make this go to 0. And because the 0 Kelvin is not possible in our universe, this is the reason why there is no 100% efficient engine can be built in our universe at all.
Okay.
Okay. And that's why conclusion is you are not allowed to steal energy from the nature 100%. No, there must be some, hardship or whatever. You have to, you cannot, your life has to be, tortures a little bit. You have to put some work into it, right? That's nothing is free. Yeah, pretty much. All right, guys, got an idea. And that now leads you back to the question that I had before the break. So is it possible for you to run an engine that eventually generates something that allow you to charge your smartphone? Yeah, let's give it a shot. If your body temperature is like 37 degrees Celsius, so you can use your body. T hot is your body here. That is just going to be, let's say, 310 Kelvin approximately. Okay. And then room temperature, T cold, that's the room. Let's give it like 20 degrees Celsius or whatever. So let's say it's going to be around 300K approximately. So now see, the temperature difference is only 10. And that's a 10 Kelvin difference under the environment of about 300K. So if you want to try to calculate the efficiency using your body as your source of the energy, is going to be 1 minus Q cold over Q hot. And the efficiency runs super small. It could be like only like, just a couple of percent. And don't forget, based on this, it means you need to have a Carnot engine operating between your body temperature and the room temperature. So in reality, the engine that you built is not going to run as a Carnot engine. So your efficiency will be even lower. So at the end, you need this, you have friction, you have, this, that, conversion into electricity, blah, blah, blah. You cannot use your body temperature to charge your smartphone. The efficiency is super low. Okay. And another thing that I can sort of, talk just for fun here is there was another idea saying that, in the sea, okay, at the bottom of the ocean, let's say, okay, the bottom of the ocean is super cold. So this is cold, but I mean, how cold can it go? Let's say it's super cold, almost water get frozen, right? So about 0 degrees Celsius, let's say. But then up top, it's a room temperature again. So it's about 20 degrees Celsius up top. So the question was, is it possible for you to build a electric plant that sort of harnessed the difference in temperature between the surface of the ocean and the bottom of the ocean? Now you see the same reasoning. No, it's just the same as you cannot use your body temperature to generate anything. Okay, as long as you're working under the room temperature environment, the difference of temperature only around 10 degrees Celsius, 20 degrees Celsius won't have anything to do with, something useful. Okay, and that's why at the end, you need a gas combustion, right? See, so you have to combust the gas and generate temperature like, 5,000 K, 6,000 K to make enough temperature difference for you to be able to extract something useful out of it with a very sort of like acceptable efficiency. Okay, sounds like that's a good conclusion that we can get out of this, heat engine studying. Yeah, sounds good. All right. Oh, there is a question comes in. All right. So there's a question comes in, say, what about in outer space? When you have a cold reservoir to be, is outer space is super cold, and you can build a very high efficient space heat engine. Correct. Yeah, you can have a lot. It's a higher efficient engine out there in the space. But I think the limit of utilize that is going to be the transport of the energy that you created in the outer space back to Earth. I think that maybe that's a problem. Does that make sense? So actually right now, even if we even had problem on Earth already, you don't have to go to outer space. The solar energy is very efficient at this point. And by the calculation, you need only a fraction of the Earth surface to gather the energy from the sun. And actually you can run the whole, world with just a fraction of the surface. But the problem lies in the energy transport. Once you get the source of the energy, how can you distribute that energy to other countries? It turns out the cost of that is super high. So it's not going to have a financial viability right there. So I think you still have a problem with the transport of the energy. So we might have to wait a little bit to have a better way to transport energy, but I still don't know how. Yeah, because sometimes something's fast and easy, but you don't have enough capacity. Like you might think of like a laser beam or whatever, but I mean, you cannot use laser beam to warm up the house or something. That's not possible. So yes, so the answer is if you build an engine in the outer space, it will have a higher efficiency and everything. But there are a lot of technical issue going on outside because don't forget, when you take into the real sort of real world consideration of the real engine over here, even though I say there's a queue code waiting for you, and then you just say, okay, right now we just connect this to the low temperature part. But in the reality, you need the heat transfer mechanism as well. Does that make sense? So like if you run like a PC computer, you need a heat sink, right? And on top of the heat sink, you need a fan to blow out the air out and all this stuff. So it means you need to, once you generate some heat, that heat need to be transported away from it. Otherwise, then you're gonna have a heat build up, and then the temperatures start to rise, and that will reduce the efficiency down and everything. So there are a lot of engineering issues that come into consideration when you really build a heat engine. So I don't know, maybe I just digress too far, but just give you a perspective of in theory, yes, going to outer space will give you a higher efficiency engine, but you might have to face some other things, something like that. That's my take on this.
Okay.
Okay. All right. Thanks for the very good question. It's very interesting. Yes. Okay. Next. Okay, guys, try this. All right, now you should be more comfortable trying this kind of sort of like it's called, I would say, just like a big question, not diving into the actual calculation of the PV diagram and everything that we saw last time yet. A Carnot engine takes 2,000 joule of heat from a reservoir at 500K, and it dumps the heat at 350K. First, what is the work done by this engine and how much heat discarded? All right, it's supposed to be straightforward for you guys now. First, let's start with the main diagram here. Q hot in, Q cold out. There's a work done from the engine. And it said this is a Carnot engine, so that's good. So let's sort of put a note on here. This is a Carnot engine. So every time you saw this in your head, Q hot over Q cold, just take the numbers, is the same as the ratio of the temperature. That's the conclusion that we got from the Carnot. Okay, now the Carnot engine takes 2,000 joule. Cool. Put it there. And it gives you the temperature. That's nice. It's 500K. And at the lower temperature that you discard the heat, it happens at 550K. That's fine. So that's it. You can see right away using this equation over here, you will be able to calculate what should be the amount of heat discarded. So let's do that. Q hot, 2,000 joule over Q cold. This is what you want to figure out. Is going to be equal to the ratio of the temperature, 500 over 350. Done. See?
Okay.
That's very easy to apply. So over here, you will be able to calculate what is the Q hot. Is going to be 350 over 500 times 2,000 joule. And that is what, 1,400, is it? There you go. Done.
Okay.
Okay, and now I can just put it here. Is it Q cold? Thank you. Yes, yes. All right. I just wanted you to see that you guys still with me or not. Okay, at this point. My bad, my bad. Just keep writing. Okay, thank you. Q cold. Q cold. There you go. All right. So that is 1,400 right there. And now you already complete the main diagram over here. You should know right away about Ajahn. That's easy. From conservation of energy, another 600 has to go to work. And that is the answer of part A. So W is 600 joule. And the heat discarded, you got it from there. It's Q cold, and that is 1400 joule. And I can actually throw in what is the efficiency of this Carnot engine, guys. Well, Ajan, no problem. Let me put a subscript C for that. Just say this is a Carnot efficiency. It's going to be 1 minus, and now pick and choose. You can do the ratio between the temperature or the ratio between the Q will be exactly the same. So let's do the Q is going to be Q cold over Q hot. And that is going to be, well, or you can just go down to the concepts of the efficiency by itself. It's the work over the Q hot, what you get over what you have to provide, whatever you like, same thing. And this is what you get. It's 0.3. You are done. Okay.
Okay.
Not bad. Okay, and this gives you and sort of like a rough idea how to calculate efficiency from unknown information. But this is sort of like, Ajahn, this is just, like algebra. It's not like a simple adding stuff, subtracting stuff, just make sure that everything just added up nicely and then you're done. I will give you more complicated problem. I think that's what you're waiting for. All right. Any questions so far? All right. Besides my mistakes there. All right, here we go. Now it's getting more real now. This is a real question. Here we go. You have a heat engine operates using the cycle shown. Now we're going to use something that we learned from last week. Now you are considering just any heat engine now, any heats, any cycles that can be represented in a PV diagram now. And then you have to figure out what is going on with this process, which comes again as a cyclic process. So what you're seeing right here in the PV diagram here is a PV diagram that showcases how an engine works. Okay, cool. All right, so that's what we're trying to do. Now, let's say the working substance is 2 moles of helium gas. All right, now your heat engine is operating using helium gas, which reaches a maximum temperature of 327. All right, let's attack this one first, shall we? So I can turn this Celsius into Kelvin by adding 273. So I'm just changing this one first into 600K. All right, just keep that in mind. We always use temperature in Kelvin scale whenever you want a pure value of the temperature. Now, assume the helium can be treated as an ideal gas. That's the only way we know how to do anyway. All right, process BC is an isothermal process. Very good. The pressure in state A and C, okay, very good. They are on the same pressure and they give this value to be 10 to the 5th Pascal. Very nice. The pressure at B is also given. Okay, very kind. 3 times 10 to the 5th. So it's 3 times higher than the pressure at A. Now, guys, go for it, shall we? This is the time. How much heat enters and leaves the gas each cycle? Woo! Huge. Oh, it's too much. Huge. Now you should be able to do this one now. If not, at least you should be able to follow what we are about to do. Guys, how much heat enters and leaves? They ask you everything pretty much. They're just asking you what is going on with the heat transfer right now, in and out from the system. Okay, let me go through all 3 questions first, right? So you know the overview of what kind of question that you're about to face. Part B, how much work does the engine do each cycle and what is its efficiency? Of course, once you found out what's going on with part A, you should be able to figure out what's going on with part B, which is the work done. And once you get the work done and all the heats involved, you should be able to calculate the efficiency. And now part C, let's compare this engine with the maximum possible efficiency attainable with the hot and cold reservoir used by this cycle. This long sentence is just saying that what if you want to operate between this high and low temperature using a Carnot engine instead? What will be the efficiency of a Carnot engine. Does that make sense? All right. So sort of like, okay, we know that this cycle won't be as efficient as Carnot engine, but what's the difference? And what if we replace with a Carnot engine? What the Carnot engine will do? That's all this question is asking you. Okay. All right, guys, attack part A first. I mean, this one I want to really go slowly because I want you guys to be able to do all this by yourself, seriously. All right, because if you know how to do this, that's it. This is a question in the exam. What else can I ask? This is what we have been building our understanding and leads toward this. Using the first law of thermodynamics, use everything that you have learned today, heat engine, efficiency and everything, and then do the full analysis of a cycle. Go for it, guys. How much heat enters and leaves the gas each cycle? All right. Oh, I have more space on the next page. All right, so let me attack part A here. So we're going to break them down into 3 segments, A to B, B to C, C to A. Why not, right? Because we have 3 different processes in the cycle here. So let's go from A to B first. All right, guys, A to B. It's easy, constant volume process, no work done. Cool. When there's no work done, the first law of thermodynamics will be delta U equal to Q. W is gone. All right, I can even write it here and just discard it out. Okay, very good. And we know even further, remember, U of an ideal gas is 3/2 nR delta T. I'm sorry, U is 3/2 nRT. So this one is going to be 3/2 nR delta T. Cool. And this one, if you remember, just a quick reminder, it's NCV delta T if you want. All right. So it means you can jump right ahead into calculating the heat in this constant volume process using NCV delta T, which is 3/2 nR delta T anyway. Cool.
Okay.
See, everything works well. And now the rest that you need to do is, Ajahn, what is the temperature difference? Okay, I can substitute number of mole, or I just leave it there. But now do you know what is the temperature from A to B? They already said maximum temperature is 600 K. Where is this temperature? Once again, in your head, every time you have a PV diagram, overlay the imaginary isotherm. All right. Okay.
Okay.
I mean, the second line is not as good, but that's what it is. So it's mean B and C are lying on the same isotherm because they said BC is isothermal. Cool. That's what it is. So now you can see, the highest maximum, I mean, sort of the maximum possible the maximum temperature that you are looking at right now is going to be the upper line. So this is 600 K. So now you know right away the temperature at B and temperature at C is going to be 600 K. T, B, and C is going to be 600 K. And now do you know the temperature at A? What will it be? Not speak well today. What will be the temperature at A? Well, then it's just the equation of states. You can compare B and A, and it's just a constant volume. So you can say, okay, let me write on the side here. P A V A over T A equal to P B V B over T B, yeah? Okay, and V cancel because same volume. The pressure at B is 3 times pressure at A. So the temperature is going to be 3 times as well. So now you can conclude the bottom temperature over here is going to be 200 K. Just 1/3 of 600 K. Cool. So with that, then you're almost done. So next, keep going. Okay, and then you do the delta T here, right? So let me write in full detail here. It's going to be T at B minus T at A, yeah? The change in the temperature is always final minus initial. So get going. 3R, 2 already canceled. T final is 600, temperature at B, minus initial temperature is 200 Kelvin. There you go. So it's it's 400 Kelvin times 3R. So it's going to be 1200 R. Just leave R there. That's good enough. And you are done.
Okay.
From A to B. So you see what we are about to do next. Yeah. And next and on and on. Try going from B to C, guys. B to C. What are you seeing over here? It's an isothermal process. When you have an isothermal process, delta U equal to 0. No temperature change, no internal energy change. That is good. So the first law of thermodynamics goes with Q is just the same as the W. And we have already seen it last time. It's going to be nRT log V final over V initial. Yes. Cool. So far, so good. And N is 2, R is R. Temperature, we already knew, is 600 K. So let's put 600 here. And log, now, what about the V? V at C and V at B. So you can do, okay, PC, VC over TC equal to PB, VB over TB.
Okay.
All right. And because they are having the same temperature between C and B, so now you can see that pressure at C is 1/3 of the pressure at B. So the volume must be 3 times. Bam, you are done.
Okay.
Isn't that cool? Log V final, which is a volume at C, over V initial, which is a volume at B, is going to be 3, log 3. So you can conclude it's going to be 1200 log 3R going from B to C. Nice. Okay. Last one, C back to A. And now you can do shortcut a little bit, Bajan. All right, I know I can use the first law of thermodynamics and everything, but C back to A is isobaric process.
Okay.
Okay, so that means I can jump right ahead into Q equal to what? What? 5/2 nR delta T. Remember that, guys?
Okay.
Yeah, because you have an isobaric, the Q equal to delta U plus W. Delta U is just 3/2 nR delta T. W is just P delta V. You turn it into nRT. You add it on top of 3/2. You get 5/2 nR delta T. Done. Okay.
Okay.
All right. So S is just NC sub P delta T. Cool. Let's go for it. And it's going to be 5/2. N is 2. R is R. Now delta T, final minus initial. Final is, yeah, you jump back to A, is 200. Initial is 600. So what is the delta T? Very good.
Okay.
Negative 400K. Yeah, stick with the sign. Stick with the sign. So over here, what you get is negative 2000 R. And you are already completed part A.
Okay.
See, the sign are automatic. When I say automatic, what does it mean? It means what you already saw up here, the 1200 R over here is already positive. What does it mean by positive heat? The positive heat flow means heat flow into the system. So now it's our time that I can do this for you. Now, okay, let me use a deeper here. Let me do here. Damn. That's the Q from A to B. It's positive. Heat flow into the system. Let me write it as QAB. All right, now let's move on to the next. Okay, let me highlight that yellow over there. As it's okay. Okay, it's yeah, orange right there. Now let's move on to the next. What about this? Yeah, it's positive. When it's positive means heat flow into the system. Bam. So it means there's a heat flow in, QBC. It's positive heat. When I say in, so it seems like I'm going to try to use the internal area to be signification of, hey, that's my inside of stuff. And when the thing's going outside, I'm going to write the arrow in the opposite direction. As is going to be for the bottom part over here. See, it's negative 2000 R. So that means going from C to E, heat leaves the system. Heat leave the system. There, QCA. Got that part, guys? Very good.
Okay.
That is it. So that's complete part A. You know exactly what is happening to the heat in each segment. Very nice. A to B, heat flow in. The reason is simple because we have already familiarized ourselves with this process so many times. It's a constant volume. The gas cannot expand. Heat flow in to increase the temperature. Yeah, that works. Yeah, we already done so many constant volume process. This is what it is. Now B to C is the isothermal expansion. So when expands of the gas without changing its own internal energy, it means gas perform works, positive work, but it cannot change its own energy. There must be some energy flow in to compensate for that work done by the gas. And that is the heat flow in, QBC. Cool. Now for the C, back to air, it's a constant pressure process. But in this case, gas is contracting along with the reduce in temperature. So the temperature of the gas is down, work done is negative. So it's, there is some compression going on, okay? But overall net, you have the leftover heat that you have to take out from the system for you to be able to lower the gas temperature down from 600K to 200K. So there's a heat flow out from this isobaric process. Isn't that cool? So that's how you interpret what is going on with this cyclic process here using first law of thermodynamics. And now, once you complete this, you are able to calculate what's next about this heat engine. Part B, how much work does the engine do each cycle, guys? Okay, how much work? So you might tend to think of like, Ajahn, work is area under the curve, right? And then, yes, you can do that one more time. You can go like A to B is zero work, B to C is area under the curve, C back to A is another area under the curve. At the end, you have already seen that the final answer will be the area enclosed by this process. That's no big deal. That is your W for sure. That is fine. However, by knowing that we are considering a heat engine, so what you're doing over here is you don't need to redo everything again because it's all conservation of energy. Can you see? One more time, guys. QAB is in, QBC is in, QCA is out. You see what I'm trying to get to here? Okay, one more time. Okay, QA, oh, I think it's lacking. Okay, so QAB is in. Okay, QBC is out, in, sorry. QBC is also in, and QCA is out. Do you see what I'm seeing over here? Yeah, it's what we just studied today. Okay, let me draw a big diagram of us that you just did today. If I draw this as a heat engine, so it's more complicated because now we have an actual PV diagram that representing a sort of like, you know, an actual how the gas has to perform during each cycle and on and on. So what you're seeing over here is you have QAB. Oh, sorry, I used orange here. QAB, that's in. Okay. And QBC is also in. And now you have Q, C, A that is out. You see what I'm saying here? And of course, Ajahn, you have one left, the W, that's the work done by this gas. So what I'm trying to sort of have you see here is, this is it. The combination of QAB and the BC that give you the Q hots. With me, guys? And in this case, there's no combination because there's only one process that give you the heats that flowing out. But if you have more than one segments that have the heat flow out, you do the same thing. You just sum them up. So what you have over here is that is your Q cold. So for part B, what you can do is the W is going to be using the same equation is heat flow in subtract heat flow out. That must be the work done by this engine. Okay, so what I can do is I can just say, take the QAB plus the QBC, those are the in. And then you subtract the QCA, that's the out. With me? And that means QAB, you just go back and then, okay, it's 1200 R plus QBC, 1200 log 3R. And then you subtract out the QCA, you just saw that it's 2000 R. And whatever it is, it's going to give you the W as well.
Okay.
Got that? Okay, so we can just utilize the, well, you can think it's still within the first law of thermodynamics, but then because now you know that this is the functionality of a heat engine and you have already worked through all the heat flow in and out. Now we know the difference between in and out must be, there's only one thing left, the work done. Okay, and it's going to be exactly the same if you were to just calculate the area under the curve, because that term is already in here. It's just already, you know, hiding. It's not even hiding. It's just there. All right, it's just already in there. Okay, cool. All right, guys. The last question of the day, part C. Compare this engine's efficiency with the Carnot engine. How would you do that? Well, Dan, this is going to be the easiest part because you can see now this engine is operating at the highest temperature is at 600. The lowest temperature is 200K. So all you need to do is just, let's say if I'm going to replace this engine with a Carnot engine, it's going to run with the efficiency of 1 minus T cold over T hot. You guys with me? And because now you know the T cold is 200, T hot is 600. So that's going to be 1 minus 1/3, and it's going to be 2/3 efficiency engine that you are looking at.
Okay.
And you are done. Okay, so I hope you seeing what sort of like this is going on in the future. It's just like you take what you have learned from the first law of thermodynamics, you know, put the heat engine on top a little bit, define efficiency a little bit, and then you just do the calculation just like what you did with the first law of thermodynamics problems. And then you just, you know, throw in some analysis that, okay, which parts of the heat flow in, which part flow out, how do you going to call this an intake, what are you going to call this an outtake, or what do you call this hot reservoir, cold reservoir, but everything is still within this main diagram. Okay, you have to steal energy from the hot, redirect part of it to generate some useful work, and throw the rest away. You are done with the heat engine mechanism over here.
Okay.
And that is it for today's, guys. Any questions? Okay, if not, then I'll see you guys on Wednesday. Yeah. All right. I hope you learned something today and keep on learning physics, I guess.